Okay, here we are where we left off last time. Last time we created our generator function and our discriminator function. Now it's time to do a little bit of setup as far as placeholders, losses, and optimizers. So let's start off with the placeholders. So we're going to create two placeholders, one for the real images that we're going to be passing into the discriminator, and then one for Z, or basically the noise, that we're going to pass into the generator. So we'll say real images is a placeholder. So TF placeholder, and it's just floating 0.32, and the shape is going to be none because that's defined by how large that batch is, and then there's 784 pixels. Hopefully this feels pretty familiar given that you've used this dataset before in the convolutional neural network section. Then for Z, what we're going to do is we'll say TF placeholder, we'll say TF float 32, and the shape here, again, none for the batch size, and we'll go ahead and feed our generator a vector of 100 random points. So once we have that, we're going to go ahead and create an instance of our generator. So we'll say G is generator. It's not really an instance, more like calling the function. And then we pass in the placeholder there. So we have our generator. We're passing in this Z, which eventually we're going to pass in with a feed function. Because remember, the generator, if we look up here, it's just a bunch of layers that eventually returns the output. We're passing in that placeholder for the actual noise, and later on, we'll pass in a feed dictionary that feeds in that noise. So generator is pretty straightforward. Now it's time for the discriminator. And for the discriminator, what we're going to do here is we're going to edit this function a little bit so that we don't just return the output, but we also return these logits here. So let's go ahead and do that. Run that again, make sure you ran that. And we're going to need to have two discriminators because remember, we want to run the discriminator first on the real images so that the discriminator is actually trained on real images and understands what the real MNIST digits dataset looks like. That way, once you start feeding it the generated images that our generator is actually trying to fool the discriminator with, it's been trained on real data and it understands what it should look like. So we're going to say D output real. So this is the real output, and then we'll say D logits real, and we're calling them real because we're going to call the discriminator function and pass in the real images placeholder. Okay, so we have the output and the logits for the discriminator when you pass in the real images. So it's going to learn on the real images. Then what we're going to do is say output fake. So we're going to call these logits fake as well because this is going to be the discriminator, except you're passing in the results of that generator. So we'll say G, and because of this, we need to say reuse equals true, because if I just do this, you end up getting a value error. So if you scroll down here, if you try to run this all again, what's going to happen, it says, hey, this variable kernel already exists, and that's disallowed. Did you mean to set reuse is equal to true in the variable scope? And that's why when we came up here, we had to say reuse is equal to true. So that's why we had to set that variable scope, because since we're running the discriminator essentially twice, we need to be able to reuse those same variable names that we've been kind of assigning here. So what we need to say here is reuse is equal to true. And that's going to take care of that issue. So that was kind of the main point of creating these scopes in order to be able to reuse a lot of the variable names. And this string is also going to come in handy later when we create a list of all the variables when we're building out our graph. Okay, so that's the discriminator. Notice how it's returning both the output and the logits because we're going to use both of those for the losses. So let's go ahead and get some losses here. So we'll say losses, and I'm going to define a basic loss function. So we'll say def loss function, take some logits in and some labels in, and it's going to return, we'll say tf reduce mean, and we're going to say sigmoid cross entropy of logits that we used before, and then we'll just say here logits equals logits in, labels equals labels in. Okay, so this is almost like a helper function. It just, I basically wrote this function so I don't have to constantly write reduce mean and sigmoid cross entropy. All right, so let's actually start calculating the losses with the use of this loss function. The first one we'll do is the discriminator loss when it's trained on the real data. So that's going to be called d underscore real loss. So the calculated loss when it's being trained on the real data. So we'll call our loss function, and then we need to pass in the logits and the labels. So we already know the logits here. Remember, that's just right here, the logits real. So we're going to pass that in. And then the second one are the actual labels. So recall that the discriminator here is not trying to be a neural network trained to detect what number it's being presented. It's not trying to tell whether the number is 7, 3, or 2. All the discriminator is trying to really understand is the image being presented to the discriminator network something that a real human being wrote, or is it something that someone like a computer is trying to pass off as a handwritten digit? So when we train it on the real data, we want all the labels to be true. So what we can do is say TF ones, and if we take a look at the documentation for TF ones by doing Shift Tab here and scroll down, this creates a tensor with all the elements set to 1. However, it takes in a shape argument. There's a more convenient, and for our case here, TF ones like, which again creates a tensor with all elements set to 1, but you can pass in a straight tensor, so you don't need to worry about the shape. So that's a little more flexible, so we'll go ahead and use that. We'll say TF1's like, and we know the shape it needs is the same as this tensor right here, so we'll just copy and paste that in. So that is the labels. Now there's one thing we're going to do here that's called smoothing. Right now, this discriminator is passing in ones as the labels, which makes sense. We're going to pass in that 1 through a sigmoid function, that's going to stay as 1, and then basically everything stays true. What we want to do here is so that the discriminator isn't so, well, to make the discriminator a little more generalized, what we can do is apply smoothing. So this helps the discriminator generalize better, and basically it just means that you reduce the labels a bit from being perfect 1.0s to being something like 0.9. So you can just easily multiply by 0.9 to apply that smoothing factor. Okay, so we'll go ahead and do that. And now let's continue on and do something similar for the fake data. We'll say fake loss is equal to the loss function that we defined earlier, and we'll pass in dlogits fake, copy and paste that in, and now instead of ones, we're just going to say these are zeros, because we know these are all fake. So now we're going to say the loss for training on fake data is to say dlogits, and this can actually be real as well. It can be fake, it doesn't really matter here. So run those two, and then we'll say the loss is equal to here, whoops, the real loss plus the fake loss. All right, so that's our total discriminator loss, and then the generator loss is pretty straightforward. You're just going to call the loss function, and we can pass in, whoops, the logits of the fake, and then we'll say TF one's like, because we know it wants to be true, so we'll say TF, this can be logits fake. Okay, so now we have both our discriminator loss by both the real loss and the fake loss, and then the generator loss. Now let's go ahead and define the optimizers. We'll go ahead and give this a learning rate of a pretty slow learning rate, 0.001. If you start going too fast, you'll basically just get a bunch of noise out from the generator. Keep in mind, as we always say, a slower learning rate means training time is going to take longer. So we're going to have two optimizers here, one for the discriminator trainer and one for the generator trainer. And in order to do that, we need to basically create a list of the variable names. So I'm going to copy and paste some lines of code here. And you typically really only do this sort of thing when you're dealing with multiple networks that are going to be interacting with each other. But you're going to call trainable variables from TensorFlow. And this just returns all the variables that were created. And by default, when you're creating these variables, they say trainable is equal to true. So we have all these variables that were created, and then inside their name, some of them are going to have DIS, and some of them will have GEN. And that's because of the variable scope. We passed in that string code here that, if you remember from variable scope, is the name. So we'll come back down here, and using list comprehension, we're going to grab every variable for every variable in these trainable variables if either DIS for discriminator is in the name or GEN if generator is in that name, and then we have two separate lists of the variables. So now that we have that, we can go ahead and create our two optimizers. So we'll say dtrainer is equal to tftrain, and we'll use an atom optimizer here, use the learning rate, and then we'll just call the minimize function here. So we want to minimize the discriminator loss, and the variable list that we're going to pass in is only the discriminator variables. Whoops, learning rate. Okay, so that's our discriminator trainer. We're going to do the very similar thing for the generator trainer. So we'll say tftrain, atom optimizer, pass in our learning rate, and then again minimize. And now we're going to minimize the generator loss. And the variable list is going to be equal to those generator variables. And if you want to explore what those lists look like, you can just do this and it'll tell you that it's a list of the variables. So you can see here kernel 0, bias, kernel, bias, kernel. Now we didn't have to do a lot of this work because this is essentially all done by the layers API. So just keep that in mind. All right, so now we successfully have created our losses and then our optimizers. So we're all ready to go. The next step is to just essentially train the session. So let's go ahead and do that in the next lecture.